Welcome to a lesson with Dr. Powell. Let's look at an example of calculating work in the following situation. Suppose that we have a rope, a pulley, and we have at the bottom of the rope a bucket. This bucket at first is full of water. And let's just suppose that that at first it has maybe 6 kilograms of water in it, and then it's leaky. So by the time it gets to the top, the bucket will be empty. All right. So it's going to go from 6 kilograms to 0 kilograms by the time it gets to the top. Let's also suppose that this rope has weight in and of itself, and that it weighs 1 kilogram per meter. And suppose that initially we are at let's suppose maybe 10 meters. So it's leaking out fairly fast. Okay, so within 10 meters, it's going to be all out. Now, it doesn't matter how fast we're going to be moving this up. The amount of work that will be done will be the same. So really, all that matters is the distance traveled and the force. Now, we could think of computing work as we've discussed before, where we have a force function. And at the beginning, what is the total force function going to be? Well, let's see, at the beginning, the total amount of force is going to be, 10 meters of rope, and you have 1 kilogram per meter. That would be 10 kilograms of rope at first. 10 kilograms of rope and 6 kilograms of water. So it's going to be a total of 16 kilograms at first. Now, how do you get force? Well, the force that we need to pull upward is the same as the force that we need to counteract gravity. So gravity is we take the kilograms, which is the mass, and we multiply it by the acceleration of gravity, 9.8 meters per second squared, and this will get us the force at the beginning. So at the beginning, if we're thinking about the force function, it's going to be 9.8 times 16. So okay, so we can let's just do it out. Okay, so 54, so 58, and then we get 9. So then we get 9, 8. Okay, just a second here. All right, so let's get that out here. All right, so we get 8, 6, 1, and 15. Okay, so we have, when this is going to be in terms of newtons now, newtons. So it looks like at the very beginning we have, if we did that correctly, so 156.8, yeah, 156.8 newtons. All right, and that's where we're starting. And then over time, it looks like that's going to go down. And so at the way end, we're also going to assume that the bucket itself has negligible weight, so we're going to ignore that. So bucket is negligible in weight. So at the end, the amount of rope, there's going to be no rope, and there's going to be no weight. So after 10 meters, there's going to be nothing. All right. So it looks like this work calculation is simply, because we're assuming linearity here, we're assuming that this we're going to assume, so I'll add this to the question, all right? We're going to assume that this leaks out at a constant rate um, per meter. So constant rate per meter, meaning this is going to come out linear in a linear relationship as it moves upward per meter. So not per time, but per meter of movement upward. So we have this. So I've actually given that to you in the problem. Say, okay, so we know that's linear. Now also, with respect to meters, now the length of the rope is itself actually goes right along with this, and so it's, in fact, it's simply the same as this x value, so that's linear as well. And so you have that the force itself is a linear function going down like this. So to compute the uh, and so because of that, to compute the work, we're just finding the area of a triangle. So to find the area of this triangle, we just have 10, and this is in meters. So Newton meters, actually another way of saying that is joules. So Newton meters, we could also say that's joules. So we have 156.8 times 10, but then divide by 2. That's the same as taking 156.8 and multiplying it by 5, since we just divide the 10 by 2, because we're finding this area here. So we get, let's see, 30 and 25 and 7 and with a point. So we get 784 joules is the amount of work that's done in lifting this bucket up while the water is falling out. Thanks for watching.